And then skip and do 7 through 9. Now, these are mastering each technique. In other words, this breaks it up for you. These are integration by parts, and the next one's partial fractions, and the next one's use substitution or something like that. And the next one's trig integrals. In other words, you've got all these techniques that you're supposed to be able to do. But as those of you who have had class before know, on the test, I'm not going to tell you what technique to do. You're just going to have a whole pile of integrals to try to pound your way through. So these are just, here's a whole bunch of integrals, have fun. You figure out which technique will work and try to get them. So in order to motivate you, since I don't collect homework, I thought we'd have a quiz maybe next Friday where I'll give you 4 random integrals. We'll count it for like 2 presentation grades. 1 or 2 presentation grades. Probably 2 presentation grades unless you all fail it, which everybody does the first integration test. That's just kind of a given, which is why I want to have a little quiz before we have the first major test that's 1 out of 3 of your tests, is because the facts are you need a lot more practice than you think you need on integration. It's like, okay, you know how to do this one if you know what technique to use. But when you've got to sit and try a technique and go, dang, and then try another technique, dang, and then realize, oh, the first technique was right, but I made some stupid mistake. You know, you've got to be a little more efficient than that when we roll around on a big test. So let's plan on having a quiz next Friday. Not this Friday, not 2 days from now, 9 days from now. My wife and I argue what the word next means. Quiz next Friday, 9 days away. And we'll count it for a couple of presentation grades. Yes. Okay. So, we skipped one problem in the notes, and Jesse had asked me about it. But I'd like to put it on the board right quick before we start putting problems on the board, just as one short example, because 1, we skipped it, and 2, it'll allow me to introduce the next section, so we know we've got plenty of stuff to work forward on. So, so I want to integrate this fella. This is one of those that you look at, and it's really almost one of the things. You're going to have to memorize some of the strategies to do them, because it's not at all obvious how to start this one. But this is one of the clever ones where you can do it with integration by parts. With me so far? That's what you did, right, Jesse? That look familiar? All right, I want to integrate this guy. I have no clue what to do. You can't rewrite it with algebra. Oh, one thing I should say in these notes over here is there's a strategy listed there for how to tackle integration. Because, I mean, really, you got an integral problem. You look at this. The first question, you just need to ask yourself a whole slew of questions. Like, do I see the derivative floating around anywhere? No, the derivative of that is this, and it ain't anywhere, right? So you know it's not a u substitution. Is there anything I can do to rewrite this? Is there some algebra I can do? No, there's no way to rewrite this. So at that point, you're really stuck. And in this case, you wouldn't even say it's a part. You wouldn't guess integration by parts because you don't see the product of 2 functions, right? But of course, every function is itself times 1. So it really, this function is dv is 1 dx, right? If I wrote it in my f prime notation, then I would say f is secant inverse of x. and f prime is 1 over x square root of 1 minus x squared, and I'd say g prime is 1 and g is x. I mean, that's the same. This is not different from this. It's just a different notation. But my point is, there is a product. It's the product of f, secant inverse of x, and 1. But you wouldn't, you don't see that and think, oh, integration by parts, x e to the x, right? When you see the integral of x e to the x, you better think integration by part, because this one's easy to take the derivative of, and this one, when you take the antiderivative, doesn't get worse.
Same way. Would it still be e to the x? The integration of e to the x?
Right, would still be e to the x, right. So yeah, it doesn't get worse because it is its own antiderivative, correct, yes. Okay, so this one's obvious, but this one's not obvious that it's integration by parts. However, if you teach calculus for 20 years, you don't forget these things. So now let's see, what's the rule? U dv is uv, so x secant inverse of x minus the integral of this times this. Okay, I'm doing great so far. Until I get to here. And then you might be doing well or you might not be doing well, depending on how much stuff you memorize from Calculus 1. Anybody recognize it? What's the derivative of x squared? 2x. Is it around there anywhere? No, so it's not a U substitution, right? It's not a reverse chain rule or U substitution. Is there any algebra I can do to that easily?
The 1/2.
Yeah, we could absolutely. That's not a bad idea. You could rewrite it as 1 minus x squared to the negative 1/2 dx. But again, still, there's no 2x around, right? Say it again louder. You could try the power rule, but then your guess would be 1 minus x squared to the positive 1/2, right? When you take the derivative, Dominique, correct? When you take the derivative, 1/2 1 minus x squared to the negative 1/2 times 2x, you got that x that we can't get rid of, right? If this had had an x on top of it, that's exactly how you would have gotten it.
Can we back up a couple steps?
Yep.
I'm wondering where the first x is.
The first x is in the numerator, and there's one in the denominator, so I cancel it.
Gotcha.
Okay, so we don't remember Cal 1. So we don't have this memorized, which is good, because I didn't want you to memorize them. I'd rather you to be able to derive them. So the next section, yeah, it's a triangle problem. That's correct. You see a triangle, don't you? The square root of 1 minus x squared just screams Pythagorean theorem at you, doesn't it? And if this x was a sine, it'd be the square root of 1 minus sine squared. Square root of 1 minus sine squared is square root of cosine squared, which is just cosine.
That's not the negative 1, right? That's
Yes, it is. It is. I don't know whether to compliment you on the usage of your smartphone or your memory. Memory, congratulations. I'm kidding. No, I can integrate this damn thing. Okay. All right. So. So if you had memorized that this is the derivative of the inverse sine function, then you would be done and you would write x secant inverse of x minus the inverse sine of x plus k. So if you were Travis and you had that one memorized, you'd go, I memorized that last semester. Ted told me to memorize these. I did. Okay. But let's say you didn't for the moment. Let's pretend that you're not Travis. You don't have his powers of memory, which so far 31 of you didn't. So I think that's a good assumption. So this is a first example of how to do what's called trigonometric substitution. And the question is, what should I let x be? The answer is there are two choices, both work. I could let x be sine of t, or x equals cos of t. I'll work one of them out. All right.
So you're showing us how to get the sine -1?
Right.
Derive it.
I'm going to derive. That's exactly right. I'm going to derive. There. I'm going to derive it, and not because, well, yes, I care that you can derive it, but it's the simplest trigonometric integral there is. And so there's lots in the homework where you do some kind of trig sub in here. You replace x with some kind of trigonometric function, and this is the simplest one of them. So we're deriving it, but we're just trying to show you the method. Okay, so what I'm going to do is let x equal sine of t, and so dx is cosine of t dt. And so I'm going to integrate. This whole thing's going to become 1 over the square root of 1 minus sine of t squared times dx is cos t dt. But since sine squared of t plus cosine squared of t is 1, cos squared of t is 1 minus sine squared of t, right? So this whole thing is cos of t squared or cos squared of t. That means the same thing, right? Doesn't matter where you write that to. Well, in that case, this is nothing more than the integral of 1 over cosine of t times cosine of t dt. So that whole thing is the integral of 1 dt. That's awesome. Well, I can integrate 1, t plus k. But now I have to go backwards because I have an integral over here in terms of x, right? This is like u substitution. You convert it to u's, then you integrate it, then you convert it back to x's, right? So I started in x's, I converted it to t's, I integrated it, I have to go back to x's. You with me, Cruz? You good?
Where did that cosine come from?
Where'd the cosine come
Yeah,
from?
1 over cosine t times?
Yes, it came from the square root of 1 minus sine squared is the square root of cosine squared. What's the square root of x squared? Back to x, right? It's actually the absolute value there. But for trig functions for the moment, we have to assume that what's in here is positive because we're taking the square root of it, right?
No, not that one, the one on the outside.
The one on the outside comes from the dx.
Okay.
Remember, dx is cos t dt.
Okay.
And so I had to replace the dx. So that was my dx. Good? Okay, but all I'm looking for here is what t is equal to. But if x is sine t, well then sine inverse of x must be t. Take the inverse sine of both sides. And there you have it.
Can you explain that one more time real fast?
Mm-hmm. X is sine t. That was the substitution I chose to make. So now I want t by itself. How do I get rid of sine? You apply the inverse function to it, right? So I take the inverse sine of both sides. So what I do is I take sine inverse of the left-hand side equals sine inverse of sine of t. But the definition of the inverse function is the one that undoes this function, right? If sine t sends you somewhere, then you apply sine inverse, you should be back at t. So the right-hand side is t, and the left-hand side is sine inverse of x. So I can replace that t by the inverse sine of x. You with me, Joshua? Good? Raven? And I know, it all looks so easy when I do it. Yes, Scorpio, what you
Go back to the
Okay. Two things. One, the whole reason I decided to use sine was because of the Pythagorean identity. So this is an identity that we know is true. Sine squared of t plus cosine squared of t is 1. That's one of our memorized Pythagorean identities. We have that memorized. Therefore, if I just subtract sine from both sides, then I get cosine squared of t is 1 minus sine squared of t, right? Now take the square root of both sides. And so what I have in here is the square root of 1 minus sine squared of t. And that's the same thing as the square root of cosine squared of t, which is back to cosine of t. It's actually the absolute value of cosine of t. But we get a little sloppy with these trig subs. You can make it all 100% precise, whether it's positive or whether it's negative. But we got enough stuff going on here without worried about that. It really should be absolute value. But you with me? Sine squared plus cosine squared is 1. Subtract sine squared from both sides. Take the square root of both sides. So this whole thing is the square root of cosine squared of t, which is cosine of t. You took something, you squared it, you took the square root of it. All right? We good? Good, Evan? No? Where are you worried?
How you get the square root of 1 over the square root of 1 minus sine t squared and got the cosine squared t.
So, right here, sine squared t plus cosine squared t is 1, right? That's a trig identity. Subtract sine squared from both sides. What do you get? You get 1 minus sine squared on this side, and you get cosine squared on this side, right? All right, I've got a 1 minus sine squared here, but I've got a square root of it. So take the square root of both sides. What's the square root of something squared? Well, not really, but it's the absolute value of x, because if you put -1 in here and you square it, and then you take the square root, you get 1 back. But if it was positive, it'd be itself. And like I said, I'm lying to you just a tiny bit, because I can make the absolute value precise, but it's hard enough without it. And you get the right answer anyway, because if we take the derivative of this, you know you get this. We know how to take the derivative of this, we did it. So we know we're right. Questions? So another thing. Yes, sir?
What made you start using trig functions from that very first one?
Okay, yeah, so this is like partial fractions. The first day I showed it to you, I showed you how to do it, but I didn't tell you how to break them up. Because that would take the rest of the hour. I want y'all to get some problems up. It's a really, really, really good question. The answer is, whenever you see square roots of things like that, it may be a trig substitution. No guarantee that it is, but it may be a trig substitution. And the reason they work is because of this Pythagorean identity, okay? One of your other Pythagorean identities is that tangent squared of x plus 1 is secant squared of x, okay? So if you happen to have a square root of 1 plus x squared that you don't know what to do with in an integral, you can let x be tangent and turn that massive ugly square root into just secant. So the answer to your question is subtle, but the answer to your question is, when I see a square root in an integral and I want to make it go away, I try a trig function that will use one of the 3 trig Pythagorean identities that I know. That's the answer to your question. I don't know if that's not a good, thorough answer, but we'll see plenty of examples soon.
So if you did that substitution, would it be the square root of secant squared, or would it just be?
Yes, it would be a square root of secant squared, which would be secant,
Oh,
because it's the square root of it squared. Okay, yes, sir.
On the top of the equal sign or the delta sign, over sign. Shouldn't that 1 over cosine be squared? Why is it not squared?
Nope, because it was the square root of the square. That's why it went away. You got it. Okay, I think y'all are in good shape to tackle some of those. Let's see what we have today for me.